Everyone. So this last slide here really is kind of wrapping up an introduction to quantum mechanics. I kind of wanted to survey the whole space of what we're talking about before we start to dig into some of the details of how atoms work and solid state physics and things like that. And so, we've kind of started with the basic first stages of quantum mechanics, dealing with photons, the de Broglie wavelength, electron wavelengths, and how those work. Moved through electromagnetism and started to understand how quantum field theory works. And here on this slide, I wanted to represent the smallest length scale that's even physically possible. Now, that might not even make sense to you. How could there be a bottom to how finely we can cut up space? But that's actually one of the consequences of quantum mechanics. And it's actually not too difficult to see why that happens. So here on the left, I've got four simple equations. This here represents the speed of light and how the frequency and the wavelength are connected together. This is just basic wave motion, and you should recognize this as the speed of propagation for a wave with a certain frequency and wavelength. This equation here represents the energy of a single photon of light. So the energy content is proportional to its frequency. Easy enough. E equals mc squared, relativity. And then here, this is the Schwarzschild radius from general relativity. So, in a sense, you have all four major branches of physics represented. You've got electromagnetism, or classical mechanics, if you want to say it that way, quantum mechanics, special relativity, general relativity. Now, if you combine all these equations together, just substitute in, this mc squared over here, juggle, you can derive this equation here, which tells us that the product of this wavelength, which is associated with the particle, multiplied by the Schwarzschild radius, is given by this formula here. And so what's going on here is that as we probe into finer and finer resolutions of distance, that requires more and more energy. Why? Because of this, right? So if I'm interested in smaller and smaller wavelengths of light, right, in order to observe something, I need to have light or something that has a wavelength that is at least as small as the thing I'm interested in, right? I want it to be smaller, actually, so I can start to use some geometric optics logic. But, at a minimum, the wavelength of the observing medium I'm using has got to be equal to or less than the resolution. So that's what this lambda represents. It's kind of a proxy for how finely I'm measuring space. But this wavelength is inversely proportional to frequency, which is directly proportional to energy. So it takes more energy to get a higher f to get a smaller lambda. So in other words, in order to probe finer and finer resolutions, it's going to require more and more energy. So I need to move from light to electrons to neutrons and things like that. In order to probe finer and finer resolutions, I need to slam electrons harder into some substrate, things like that. Problem with more energy is E equals mc squared. So the more energy I use, the more mass that object has, which has a secondary effect of disturbing the thing I'm interested in, but also, kind of in an extreme sense, not kind of, but in an extreme case, the more mass I have, the more energy I pour into this material in order to observe finer and finer resolution. Eventually, the thing I am using becomes a black hole. It collapses on itself due to general relativity. and that is the boundary. I can't use black holes. Basically, I've poured so much energy into the system, it collapses. This is the boundary layer. This represents how deep I can go. And so if you take this quantity here, this is all, 2, doesn't matter. But, this gives me an order of magnitude, right? If I take the square root of this to basically represent this length scale, this number here represents, in principle, the finest level of resolution possible given the laws of physics, I know. I cannot measure something smaller than 10 to the minus 35. So, that offers an interesting conundrum. Because I said earlier that the reason we are forced to use superposition in our quantum mechanics is because we shouldn't be allowed to use a theory which assumes that's based on assumptions that are actually impossible. So if I cannot, in principle, distinguish two electrons from one another, I shouldn't build my theory based on this. Well, what I'm saying here is that we have a fundamental length scale with which we cannot probe any deeper. However, general relativity, classical mechanics, even quantum mechanics are all based on the assumption that space is infinitely divisible. So how these things reconcile, no one really understands. But there is something fundamentally impossible occurring here when we combine quantum mechanics, relativity, general relativity all together into one master theory. We end up with something that is that gives us pause to recognize that there is some sort of limit here, and that our theories at a fundamental level still require some form of refinement, and that is what is driving, the bleeding edge of physics today.